Assalamu alaikum everyone. So this is our lecture 8, and in today's lecture we'll be discussing about the complete solution of ax equals to b. So in the previous lecture we actually solved we saw how to find the null space of any matrix, and today's lecture would be seeing the complete solution of x equals to b. So if you could remember, in lecture 4 we solved or we saw the approach for elimination, okay, Gauss-Jordan elimination. So it is like one step for solving ax equals to b, but we didn't go through how to solve the equation x equals to b. Okay, so elimination is just one step towards the solution, and we'll see the rest of it today. Okay, so let's say you have this system x1 plus 2x2 plus 2x3 plus 2x4. So you have 4 variables and 3 equations. Let's say this one is b1, and 2x1 plus 4x2 plus 6x3 plus 8x4 equals to b2, and the last equation is this one. So these are the 3 equations and 4 unknowns, so you have to solve it. Okay, so if you could remember that if we have any linear system of equation, we need to make an augmented matrix from it. Okay, and the augmented matrix would be 1 2 2 2 2 4 6 8 3 6 8 10, and these are the coefficients. Okay, so how to augment it? You just need to connect the right hand side. Okay, so my question here is, can we solve this linear system equation for any b1, b2 or b3? The answer is no. So this b1, b2, b3, this vector has to be in the column space of A. Then only then we can solve this right hand side, right? So we know this from our previous lecture where we discussed about the column space. So after multiple steps, so let's go through the steps. So we need to make the elimination, we need to find out the pivots, we need to make the other rows 0 or other positions 0, and try to get an upper triangular matrix. The matrix will not be triangular here. We will not get an upper triangular matrix here because it is a rectangular matrix, but we will get upper something matrix. Okay, so so you already know eliminations. Okay, let's go through the steps. So this should be, so I need to make this entry 0 and this entry 0, and towards that I have to make two operations. Okay, 2 operations would be r2 minus r1 into 2 and r2 minus r1 into 3. So I'm not going into the details of elimination because you already know it. So this would be 1 2 2 2 0 0 2 4 0 0 2 4, and this would be b1 b2 minus 2b1, then b3 minus 3b1. Now I have to, as this is a pivot, I need to make this entry 0. So how do I do it? What I need to do is, okay, so I have to do is I have to just subtract row 2 from row 3, and I will get 1 2 2 2 0 0 2 4 0 0 0 0, and this would be b1 b2 minus 2b1, and if you subtract second row, that means this one from this row, you will get b3 minus b2 minus b1. Okay. So the solvability condition here, as I said, that you cannot solve for any b1 b2 b3. You already have got, or we already have got one solvability condition from here, and that solvability condition is, as you can see, all the coefficients are 0, and if you have any value other than 0 at the right hand side, then this cannot be solved. Okay, so the solvability condition here is b3 minus b2 minus b1 has to be 0. That means b3 has to be the summation of b1 plus b1 and b2. Okay, so any characteristic with this, or any property with this equation can be solved by this system. Okay, that means we can solve 1 5 6, we can solve minus 2 minus 4 and minus 6. Okay, so this type of systems can be solved. So these are the values of b's. Okay, so basically the summary is ax equals to b will be solvable when b is in the column space of A. Okay, so if a combination of rows of A gives you 0 row, just like this, like the third row is basically the combination of this one and this one, the row 1 and row 2, right? This row 1 and row 2, if you add these two rows, you will get the third row. So if a combination of rows rows of A gives you 0 row, then same combination of the entries of B like must give you 0. So and if it gives you some other values than the 0, then you'll have to maintain the same ratio or the same combination for the entries of B as well. Okay, so now I have to find the complete solution to Ax equals to B. Okay, so we have two steps to find the complete solution of Ax equals to B. So the first step is, or step 1 is, find x particular, which is also known as xp. So to find x particular, you have to set all free variables to 0. Okay, so what was our augmented matrix? Our augmented matrix was 1 2 2 2 0 0 2 4 0 0 0 0. Okay, and let's take a real value. We just use b1, b2, b3 to find the solvability condition. Now let's solve for a real value. Let's say we'll be solving for f156. So if we have 156, the augmented matrix would be what was the last if we have 156, then this would be 1, this would be 5 minus 2 into 1, then this would be 3, and this would be definitely 0. So 130. So the last thing would be 1 3 and 0. Okay, so which are the free columns here or free variables here? So this one is a free column and this one is a free column. Okay, so these are the free columns. That means our x2 and x4 are the free variables. So the two equations from here would be x1 plus 2x2 plus 2x3 plus 2x4 equals to 1, and 2x3 plus 4x4 equals to 3. But the condition is you have to make, or you have to assign all free variables to 0. So this would be 0, this would be 0, and this would be 0. So our two equations would be x1 plus 2x3 equals to 1 and 2x3 equals to 3. So from here, one x particular would be, from here we would get x3 equals to 3 by 2, and if x3 is 3 by 2, then from like switching the value of x3 here would get you x1 equals to a negative 2. So our one particular solution would be minus 2 0 3 by 2 0. So x3 is 3 by 2 and x1 is negative 2, and the other two free variables are 0, as you can see. Alright, so this is our one step. The first step is done. The second step is, okay, so this is our first step. Yeah, so our step 2 is the complete solution to ax equals to b is x particular plus x of n. Now this x of n is basically the null space of A. Okay, so what is the logic behind this? The logic is, so x complete is basically x particular plus the null space. The logic is A, so difficult, A multiplied by the x multiplied by the particular x particular actually gives you one particular b, right? And if you multiply a matrix with its null space, basically you would get 0, because it was the main point of solving the null space of any vector, right? null space is basically this all the solutions of Ax equals to 0, right? So this is the null space, and if you add these two things, then you get xp plus xn equals to vector b plus the 0 vector, which is b, right? So this is the main logic behind this, that if you add x particular with the null space, you will get the complete solution for Ax equals to b, okay? Because Ax like xn is the null space, and like it doesn't contribute anything new to this x particular, but it adds a lot more solutions to the solution space, okay? This is definitely not a subspace, but we call it the solution space, but it is not really a space, okay? So the null space of this matrix, we solved it in the previous class. So the null space was the null space of this vector, this matrix was which matrix? This matrix. The null space, just please refer to the last video, which is lecture 7. So it was basically, if I'm not wrong, one solution was -2 1 0 0, and another solution was 2 0 and -2 and 1. So the null space was, so these were x spatial, so these were the spatial solutions, and the whole null space was all the linear combinations of it, okay? So this is null space. So the complete solution is xp plus xn. So xp or x particular is -2 0 3 by 2 0. We just solved it, and the null space is c -2 1 0 0 plus d 2 0 and -2 and 1. So this is the complete solution to Ax equals to b. Now if you have any confusion in your mind, just take any values of c and d and add the whole thing here and multiply with a, and you'll see that you will get b, okay? So please do check it if you have any sort of confusion. Now one question may arise that what is the difference between x particular and x spatial? Well, x particular is a solution when b has a non-zero value for Ax equals to b, and x spatial is for Ax equals to 0, okay? Now like one point should be noted here, that while solving for x particular, all free variables must be set to 0, okay? And for x spatial, all free variables all free variables are set to 0 except 1. So or it can be rewritten as one of the free variables must be set to 1. Okay, so I hope you remember this from the previous lecture. So this is like the way to find the complete solution for x equals to b. Now I'll give you one system of equation for x equals to b, and you have to find out the complete solution for that, if it exists. Okay, if I give you such a b that it doesn't fall inside the column space of that particular matrix A, then you cannot definitely solve it, right? You cannot solve it. So in that case there would be no solution. Just here, if it wasn't 1 5 6, if it were like 1 5 3, then it doesn't fit with the solvability condition. So in that case you cannot solve that system of equation. Okay, so I need to show you the bigger picture here, like when we can solve, or in which conditions we can solve, or how many. Oh, one thing I forgot to mention, we got x complete equals to xp plus xn, right? So the solution was basically -2 0 3 by 2 0 plus the whole null space, which was okay c into -2 1 0 0 plus d into 2 0 -2 and 1. So how many solutions are there for x equals to b? What is the, like, what numbers or how many solutions you can get from this combination? The answer is infinite amounts of number, right? So you can get infinite solutions from here, because you can set any values to c and d, and for that you get one solution. So there are infinitely many solutions here. Okay, but there can be a case, there might be a case where the right hand side b doesn't fall inside the column space. Just the example that I just showed you, like for the combination of 1 5 3 here, so there might be no solution here. So we will see that in which conditions we will get infinitely many solutions, in which conditions we cannot get any solution, in which conditions we can get maybe one solution. Okay, so this is the bigger picture. Okay, so think about a matrix, think about a m by n matrix of rank r. Okay, so what is the relation between r and m and r and n? So what's the relation between r and m and r and n? So the answer is, think on this, that the rank, that means the pivots, right? So there might be if you have a 3 by 3 matrix, then you might have 3 pivots, right? Or let's say you have 2 by 4 matrix. In that case, you can have at most 2 pivots, not more than that, right? So it cannot really cross the limit of rows here. So R might be equal to m, or it can be less than m. Okay, the same goes for n. If you have a 1 by 3 matrix, then you'll have a maximum of 1 pivot, not more than that. Okay, because you have only 1 column. So the same goes for R and n, that R might be equal to n, or it should be less than that. Okay, so these are pretty easy things. If you cannot understand it, please take 2 or 3 examples and think about those matrices, and you will see that these 2 conditions are true. So there might be a few cases here when we talk about the ranks and the number of rows and columns. Okay, so let's go for case 1. So take one example for case 1 where the matrix is full column rank. That means R has the same value as n. That means there are, let's say, n columns there, and every column has a pivot. Okay, every column has a pivot. For example, let's take this matrix A equals to a tall and thin matrix 1 2 6 5 and 3 1 1 1. So these 2 columns are independent. Why this is independent? Because column 2 is not a multiple of column 1. So this is definitely this column is definitely independent here, and you'll get 2 pivots on 2 columns. Okay, so there are n pivots in this kind of matrices. Okay, so in this case, all these columns are basically pivot columns, and there is no free variable. So if there are no free variables, think on this, that if you have no free variables, you cannot set like 1 to any of the columns, right? So if you cannot set 1 to any, like while solving for the null space, so if you do not have any free column, so in that case you cannot assign 1 to any of the column. So you will only get one solution for the null space, and that is n of A equals to 0 0 0 0. Okay, so the 0 vector. Okay, so the size may be different, so this means the 0 vector. So you'll have, so the null space is basically empty, not empty, you'll have only 0 vector, but let's say this is empty. So as the null space is empty, so the solution of Ax equals to B, in that sort of solution, for Ax equals to B, you will have only xp, right? If you had xp plus xn, well, this is xn, and this null space wasn't empty, it had a space, a subspace, then you will get infinite solutions, right? But in this case the null space is empty, so you'll have only one solution, and that is xp. Okay, so you'll get one unique solution if it exists. Okay, so this is one unique solution, unique if exists. Okay, there might be a case where B is not inside the column space of this matrix, and if that is not inside the column space, you cannot solve it. Okay, so if you do elimination, you can get this sort of row reduced echelon form. You'll get this sort of entries in this matrix. So you can write this as I, because this part has a very similar structure to the identity matrix, and you'll have 0 at the bottom. Okay, so the summary here for case 1, so for case 1, the summary is if a matrix is full column rank, then you'll have like all columns of A are pivot columns. There will be pivots in every column, but 2 would be there are no free variables, there are no free variables that means no spatial solution, that means the null space is basically the 0 vector. Okay, and the last point is if Ax equals to B has a solution, though it might not. Okay, though it might not, then it's the only solution. It's the only solution. Okay, so this is the summary for case 1. Okay, so let's go for case 2. So case 2 is, let's say the matrix is full row rank. Okay, that means R number of pivots R is equal to the number of rows, and let's say M is less than or equal to N. Okay, so so in this case every row has a pivot, so that means the rows are linearly independent. Okay, so one example can be, let's say you have this system xy plus z equals to 3, x plus 2y minus z equals to 4. So from this you will get 1 1 1 1 to negative 1 So 3 4, and from this if you do elimination you get 1 0 3, then 0 1 negative 2. So I have done the row reduced echelon form here, and 2 1, and this particular structure here has a very similar form to the identity matrix, and this is the free column. Okay, so you can write this as I if. Now there are some points here. The point is, as you can see that okay, so I have solved the solution here. In the right hand side you have 2 1, so please do it on your own. That in this case x particular is 2 1 0, and x n is c of minus 3 2 1. Please check if this is correct or not. I've solved this. Okay, so in this case, like, all the rows have one pivot. Okay, and the null space is not empty, so there would be one solution for every b. Okay, or ax equals to b has a solution for all right hand side b, because as you can see, like, all the rows are independent here. So you'll have no row that is combination of any other row. Okay, so in that case you'll have one pivot for every row, and if you have one pivot for every row, that doesn't like that. So in that case, if you have any b, then all the entries of b, like the entries of b, do not have to depend on any other element. Okay, so let's say you have anything 5 6 or 9 10, then these entries will not have to depend on each other. So which we saw in the first example, that that b3 had to be equal to the b2 plus b1 to be solved. Okay, so there is no solvability condition in this case, and as there is no solvability condition in this case, so there would be solution for every right hand side b. Okay, so I hope I could make this point clear. So if a matrix is full row rank, then all rows have pivots. 2 is this one, like ax equals to b has a solution for all right hand side b. For 3 so we can say that the column space is the whole space Rm. So in this case this is R2 because there are two rows here. So why this is the case? Because as you can see, you have two pivots for two rows. Okay, and if let's say this is a 5 by 10 matrix, so in that case you will have 5 pivots for 5 rows. So it means that the column space can span the whole of the row space. So only for that, this Ax equals to b will always have a solution. Okay, and what about the null space? The null space is not empty. Okay, the null space is not empty. So because there are free columns here, as you can see, this is a free column, this one is a free column here. So as there are free variables, how many free variables? So there are n minus r, that means n minus m, because r is equals to m, number of free variables. So as there are n minus r free variables, there should be n minus r spatial solutions as well. So there are n minus m spatial solutions in n of a. So in that case, how many solutions would be there for Ax equals to b? See here that you will always get a solution. You'll always get a solution for Ax equals to b, right? And the null space is not empty, so always the solutions, the number of solutions would be infinitely many, because you can take any vector from the null space and add it with the particular solution. So in this case, the complete solution is basically xp plus xn, and whenever you have this solution where xn is not empty means no other vector other than 0, then you'll always get infinitely many solutions. So you'll get infinitely many solutions for this sort of structures. So okay, so the fifth point is there are infinitely many solutions for Ax equals to b. Okay, so now we have come to case 3. So case 3 is full rank matrix, where the rank is equals to the rows and the columns. So we have a very beautiful structure of the matrix. That means the matrix would be either 3 by 3 or 4 by 4. So the number of rows and number of columns would be same. So in this case A is invertible. So whenever you have an invertible matrix, the null space is always 0, because there is no dependent column. Okay, so that means we'll have, let's say you have a 3 by 3 matrix. So you have this one, these edges, and these columns are not, so there are values for these cross signs, and no column is dependent on any other column. So the row reduced form of this would be 1 0 0 0 1 0 0 0 1. Okay, and as you have this structure, there would be no solution for the null space except the 0, right? So if as you have a full column, a full rank matrix, that means like you can reach out to any point. You can reach out to any point in the respective dimension. Okay, that means the column space actually span the whole space or the whole vector space. So whatever combination of B you might take, you'll always get a solution, right? So you'll get one unique solution for every B. Okay, so the summary here is one unique solution for every B. Okay, you'll always get a solution because the column space actually spans the whole vector space, right? As we saw that I can span the whole vector space. So you have the structure is basically I, right? The identity matrix. This identity, you can get like any point in the vector space with this I. So you can reach out to any point here by the help of this matrix. So if I want to summarize, or if I want to make a table, let's say, so this is the summary table. Okay, this is the summary table. So this is what should be the row reduced echelon form after elimination, and the number of solutions for Ax equals to B. Okay, so there might be 4 cases. So first, let's say the matrix is full rank matrix, R equals to n equals to n. Second, let's say this is a full column matrix. Third, let's say this is full row matrix. And fourth, let's say the rank is less than m and less than n as well. So let's solve the first 3 cases first. So in case of R, M and N, we saw that the row reduced echelon form might take the structure of I. So it is I, and how many solutions are there? So there is one unique solution for every B. So the number of solution is exactly 1. Okay, in case of full row rank matrix, in case of full column rank matrix, we have, so in case of full column rank, and this is full row rank, we have this structure of row reduced echelon form, right? And what was the number of solutions? So in case of full column rank, there might be one solution if it has one solution, and we saw that the null space is 0, so you cannot add anything new to the particular. So there's the only solution if there is any solution, right? So the thing here is, if it has the rank is same as the number of column, then it will have the structure for R, and there might be 0 or 1 solution. in case of full row rank matrix, we saw that it has the structure of this one, and as you have the full row rank and the null space is not empty, then you will always have infinitely many solutions. We saw that in case 2. So in case 2 it was full rank, the structure was this, and we had x complete, and as there are free columns, the null space is not empty. And in case of this one, the fourth condition, we have basically this and this condition combined. Okay, so you might have this structure, and the number of solutions can be either 0 if there is no solution, and if there is any solution, the null space is not empty. Okay, because as there are free variables there, so it can be 0 or infinitely many solutions. So if there is any solution, then it would be infinitely many solutions, because the null space is not empty. And if there is no solution, then it is 0. Okay, so I'll finish with one example today. That the example is find all solutions depending on B1, B2 and B3. So let's say you have this system of equations. Okay, so if I make an augmented matrix, I'll get 1, negative 2, negative 1, negative 2, negative 2, 2, negative 5, minus 4, 4, negative 9, negative 8. And if I augment it, B1, B2, B3. So from here, if I do elimination, please do it on your behalf. So I'll get row reduced echelon form as 1 0 0. There will be 0 1 0, and there will be a negative 2 0 and a 0 here. So in this side it would be 0 2 B1 minus B2, 2 B1 minus B2, and it would be 5 B1 minus 2 B2 at the end. Okay, so we need the condition here, so I have to write the, okay, just erase it, and what I will get is, I will, please do the whole elimination by your own. So 1 0 0, you'll get minus 2 minus 1 0, and you'll get minus 2 0 0. You'll get B1 here, you'll get minus 2 B1 plus 2 plus b2 here, and you'll get negative 2b1 minus b2 plus b3. Okay. Now after that you will get that matrix. It will be basically 1. If you go for, so this is the upper triangular matrix here, and this is the 1 0 0 0 1 0 negative 2 0 0. So this is the row reduced echelon form here, and you will get 5b1 minus 2b2, 2b1 minus b2, and we have a negative 2b1 minus b2 plus b3. Okay, so you know the solvability condition. Okay, so it says that find all solutions depending on b1 b2 b3, and what is the dependence here? The dependence is this. So minus 2b1 minus b2 plus b3 has to be close to 0, right? So this is the solvability condition. Now what is the structure here? The structure here is I0, because it has I here. There are free columns there, so F, and there is a 0 column. So there should be either 0 or infinitely many solutions. When there would be 0 solutions, if it does not fulfill this condition. If this condition is not fulfilled, there are 0 solutions, and if this condition is fulfilled, then we have so we have x particular for ax equals to b, for ax equals to b. Here b is solvable, that means it fulfills the condition we just wrote. So in this case, the solution x particular would be, the solution would be 0, which is this one, 2b1 minus b2, and no, this should not be the x particular. So there is an x particular. Okay, and the spatial solution is, ax equals to 0. So basically we have to make the free column equals to, the free column should be equals to 1. So x spatial would be okay, so from here it is x1 minus 2x3 equals to 0, and x2 equals to 0, right? And the free column is 1, so this has to be assumed as 1. So x2 is 0, x3 is 1, and x1 is 2. So the spatial solution is 2 0 1. Okay, so the x complete is basically xp plus xn. So xn is basically xp plus c into xs. So xp equal to c into 2 0 1. Okay, so this is the particular this is the complete solution for the system given here. Okay, now can we actually make conditions, or can we imply conditions on xp? So okay, I think this is the this way to solve it, but okay, can we get a solvability condition from here? Let's work on this. So we have x1 minus 2x3 equals to 5b1 minus 2b2, and another equation would be x2 equals to 2b1 minus b2. So for particular solution, the free variables should be set to 0. So x3 is 0. So for xp we got x3 equals to 0, x2 equals to 2b1 minus b2. So you have to find the solutions depending on b1, b2, b3. So there is only b1, b2, b3 here, so you can say that x2 is 2b1 minus b2, and x1 is, as this is 0, x1 is this one, so 5b1 minus 2b2. okay, so we solve the xp. So our xp here should be 5b1 minus 2b2, then 2b1 minus b2, and 0. Okay, so now we have solved it completely. Okay, x complete is basically this one. So if I give you this sort of problem, you should be able to answer in this manner. Okay, so this was a long class, so I didn't want to break this into two parts, because there would be some you face problems to refer to the previous lectures then. So this is the complete lecture on the complete solution of Ax equals to b. So in the next lecture you will see how to find out the basis vectors, the independence factors, and some other topics. Okay, so see you in the next class, inshallah. Assalamu alaikum.